right, can you all hear me? Awesome. Yeah, so I'm Emily. I'm a grad student at Caltech and also a pre-doc here at the CFA. And I'm really excited to share some work that I've been doing with a group of wonderful collaborators, which is focused on understanding the X-ray signatures of galactic feedback processes in numerical simulations, with a particular emphasis on applying this to predictions for the next generation of X-ray observatories. So as many of us are aware, the morphology and the kinematics of the CGM, when predicted by numerical simulations, is hugely dependent on your choices for galactic feedback physics and also your implementation. So in order to understand this, we've selected a sample of about 20 galaxies, which are all roughly Milky Way mass at z of 0, from 5 different suites of simulations. And so all of these simulations incorporate very different feedback processes in them. So firstly is illustrious TNG, so TNG 50 in particular, which incorporates its prescription for stellar and AGN feedback. We have some galaxies from Fire 2, which have their own description of stellar feedback, as well as some Fire 2 galaxies which also incorporate cosmic ray feedback, as Sam was talking about a couple talks ago. We have some Eagle galaxies, which have their descriptions for stellar and AGN feedback, and we also have some galaxies from the Foggy Simulation Suite, which has a stellar feedback implementation. Yeah, and so the goal is to both identify and begin to understand how these different X-ray probes of feedback, as exhibited by numerical simulations, can help us prepare for the design of the next generation of high-resolution X-ray observatories, particularly those with microcalorimeter spectral resolutions. And so the first sort of obvious X-ray probe that we can use for this is the X-ray surface brightness. So in particular, a broadband X-ray surface brightness from about 0.5 to 1 keV. And so here I'm showing 6 different galaxies from the 5 simulation suites. All of these are roughly Milky Way mass galaxies. So on the left, we have the 2 Fire galaxies on top without cosmic rays and on bottom with the cosmic ray prescription. Then we have an Eagle galaxy and a Foggy galaxy in the middle, and 2 TNG galaxies on the far right. And so I'm going to play these movies, which are going to show the X-ray surface brightness in the soft energy band, just sweeping around in viewing angle. And so you can immediately see differences in what the X-ray predictions and surface brightness are for these different galaxies. The morphologies are very different. I'll play this again. So in TNG, we have these very extended, very diffuse halos. We've got lots of substructure going on. In contrast to that, the Fire galaxy with cosmic rays has very, very little X-ray emission. We don't see strong evidence for that hot gas halo like we do in other simulations. And so in addition to looking at the broadband X-ray surface brightness, which existing observatories are fairly sensitive to, when you have a microcalorimeter, you can begin to isolate different lines in surface brightness. And so here I'm showing an example of one of the Foggy galaxies. This one's called Blizzard. And I'm showing 3 different X-ray surface brightness maps here. But instead of being from 0.5 to 1 keV, these are just in particular X-ray emission lines. So these lines are 07, 08, and iron 17. I've listed their energies there. And these are lines that are fairly bright in Milky Way mass halos. And at Z of 0.01, they're shifted very nicely away from the Milky Way foreground emission lines. And on bottom, I'm just showing the radial profiles for each of the corresponding maps. Some interesting things to note here are that in 07 and 08, the lower energy X-ray emission lines, you can see that you're really probing this volume-filling gas out to several hundred kiloparsecs. Whereas if you look with, for instance, iron 17, you're tracing these very hot, higher velocity and very high surface brightness outflows associated with the feedback in the galaxy itself. And so the emission line that you're actually using to probe the surface brightness or the morphology is going to make different predictions for what your galaxy is going to look like. And this holds true in other galaxies in the sample as well. So here's an example from TNG 50, so 07, 08, and iron 17. And you can see again that 07 and 08 tend to trace this volume-filling, very diffuse gas associated with the hot CGM. And then the iron 17 starts to probe these higher surface brightness bubbles, which are associated with the AGN feedback incorporated in those simulations. So your choice of emission line is going to make very different predictions for the morphology of your galaxy in the soft X-ray band. In addition to surface brightness, we can also start thinking about making maps of the line-of-sight velocity structure of the CGM. With a microcalorimeter, you'll be able to isolate those velocities and make maps using particular emission lines. So here, I'm going to show the same movies, but instead of projecting surface brightness, I'm projecting line of sight velocity for these galaxies, weighted by the X-ray emissivity. And so moving around, you can see that the kinematics predicted by each of these simulations are very different as well. So in TNG, you can see these huge bubbles and outflows being driven by the AGN feedback in the galaxy. You can see some very nice outflows in the foggy galaxy as well. The fire, canonical fire, and the Eagle galaxies, they show a pretty good transition from disk rotation to global CGM structure. And then you can see the Fire 2 galaxy, which incorporates cosmic rays, sort of has this disconnect between the rotation that you see in the disk versus what you see on large scales in the CGM. And so as we did with surface brightness, we can also start to look at these in different emission lines. And in particular, one way of visualizing this is by using a radial velocity profile in cylindrical coordinates. So if you imagine you have a disk galaxy here, and you plop a cylinder down on top of it, you azimuthally average radial velocity, and you paint that onto a 2D map, you can sort of isolate what the outflows are looking like with respect to the inflows. So for instance, in this TNG galaxy, you can see there are these huge biconical outflows above and below the disk associated with the AGN, whereas the inflows are largely concentrated in the disk plane. And so as with the other velocities and the surface brightness, we can weight this by emission lines, and we can make comparisons between the different galaxies. So I'm showing here 5 different galaxies, 1 galaxy from each of the simulations. And I'm showing these radial velocity profiles weighted by individual X-ray emission lines. So with O7 on the top, moving down to iron 17 on the bottom. And immediately there are several interesting things that you can pull out of this. Firstly are these biconical outflows that are super apparent in TNG, and this holds true for most of the TNG galaxies as well. And then one of these foggy galaxies, Blizzard, has a similar outflow structure above and below the disk associated, we think, with the implementation of stellar feedback in that simulation. You can also see that if you compare the magnitudes of the velocity structure as traced by O7, the lower energy emission line on top, and iron 17, the higher energy emission line on the bottom, that the higher velocities are traced by these higher energy emission lines. So in TNG, you can see that the magnitude of the biconical outflows is higher when you trace with iron 17, which means that even within the hot phase of the CGM gas, which emission line you're using is going to be probing a slightly different temperature or velocity structure. You can see this as well in the Eagle galaxy, it's pretty apparent, as well as the foggy galaxy. Another thing you can do is you can start to make these global edge-on profile comparisons between the different galaxies. So here I'm showing 3 different quantities. All I did was I made an edge-on projection of each galaxy in the sample, and I took radial profiles of them. So on the left, we see X-ray surface brightness. Most of the galaxies show fairly similar shapes and normalizations in X-ray surface brightness, with this exception of the Fire galaxy, which incorporates cosmic ray physics, where we don't see a lot of high surface brightness X-ray emission coming from that halo. And that's because your non-thermal pressure support is coming from the cosmic rays rather than thermal pressure support from the hot gas. Temperature, a fairly similar story. You can see that within the galaxies which exhibit higher temperatures, TNG shows generally the highest temperature profiles. Thank you. Highest temperature profiles, which is consistent with this picture of these high velocity, high temperature biconical outflows from the AGN. And then the Fire galaxies have sort of lower overall temperature profiles here, with the Eagle and the foggy galaxies falling in between the two. And it's a similar story when you make radial profiles of the velocity dispersion along your line of sight. So the TNG velocity dispersions are highest because of these outflows, and the Fire cosmic ray ones are lowest. And so all of this is really fun and interesting, but we really need the next generation of X-ray observatories to be able to make these measurements and potentially distinguish observationally between the different feedback models which are incorporated in our state-of-the-art simulations. In particular, we need microcalorimeters in space with sufficient spectral resolution to map these lines individually. And so I think John Zuhone will be giving a talk later today about the different future X-ray observatories that are coming up. I'll mention here LEM, Athena, LYNX, and HUBS as potential prospects for that. So in summary, the feedback choices that you make in your numerical simulations can predict very different X-ray morphologies and kinematics in the CGM that are potentially observable with the next generation of X-ray observatories. In particular, different X-ray emission lines, even when they're only separated by about 200 eV, can trace different phases of the hot CGM gas in these galaxies. And we're currently doing a sort of full-scale parameter space exploration of these X-ray signatures in order to inform our design and our preparation for next-generation X-ray observatories. Yeah, so with that, I guess I'll take any questions.
Fantastic talk. I'm curious, so you made a very good point for these future X-ray missions. I'm curious if there are any existing X-ray observations that could maybe help constrain for the simulations what sort of feedback methods should we use?
Yeah, definitely. You can, I think at CCD resolution, you can definitely make statements about, like, for instance, global X-ray surface brightness profiles for stacks of galaxies. So it's very difficult to do this on a galaxy-by-galaxy basis in the X-ray band. But you could, and some people, I believe, have compared, for instance, Illustris and Eagle to the Ebers-Zeta stacks. So you can constrain global X-ray surface brightness profiles for stacks of galaxies on a population basis. But to my knowledge, yeah, in order to make these individual galaxy-by-galaxy sort of spatially resolved predictions, you really need a high spatial, high spectral resolution instrument. And so CRISM, for instance, is wonderful in terms of spectral resolution. It's a microcalorimeter, it's on the sky right now, it's really exciting, but its spatial resolution is incredibly poor. Yeah, great question.
Since you mentioned CRISM, you talked to us about launch side velocity, but not about turbulence at all.
Yeah.
So you looked at all, do these different models generate different levels of turbulence in the hot CGM?
It's a great question, and we have not explicitly looked into that.
You should, because Lem would also be able to tell us about that.
Yeah, that's a really good point.
More question? Okay.
I really like the idea of looking for iron 17 emission. Do you know if that's been seen with Chandra or XMM? I know there's a lot of work on 07 and 08 emission already, but the iron 17, has that ever been seen in the CGM? Or
That's an excellent question as well. I know of iron 7 and iron 8 as well. I don't know to what extent iron 17 has been observed in the CGM. I know it's much fainter of an emission line than 07 and 08. So my intuition is that it would be much, much more difficult to observe with existing telescopes if it has been. Yeah.
And also mixed with many other lines in that particular line as well.
Yeah. At Z of 0.01 for a roughly Milky Way mass halo, you're sort of offset enough by redshift to isolate it, but it's much more difficult than for 7.
Okay, maybe one more question. And the next speaker, come up and prepare. Okay, there's no more question. Thanks to the speaker again.